So I will tell you about construction the Voronoi diagram by sweeping, which is Fortune's algorithm. It is a sweep line algorithm. Its time running is n log n, as we will prove it. It takes linear amount of space, and it was originally published by Stephen Fortune in his paper called A Sweep Line Algorithm for Voronoi Diagrams over 30 years ago. So let's recall what is the sweep line algorithm in general. So the strategy in a plane sweep algorithm is to sweep a horizontal line from top to bottom over the plane. While the sweep is performed, we keep the information maintained regarding the structure that we want to compute behind us. Let's say behind us. And while the sweep line moves downwards, the information does not change except at certain special points, the events. But how can this be done with computing the Voronoi diagram? Because the problem is as follows. When we go from top to bottom, we first encounter the vertex that is not yet computed because it's defined by the site that we haven't visited yet. So how can we exactly know about it before encountering the site? Well, very fortunately, Stephen Fortune had a solution for this, and this solution is a pitch line. And this idea is really amazing. We will have to apply this sweep line paradigm, but in a slightly different fashion. Because instead of maintaining the intersection of the Voronoi diagram with the sweep line, we will maintain the information about the part of the Voronoi diagram of the sites above the sweep line that cannot be changed by sites below it. But the question is how to distinguish which part cannot be changed. Well, for this we have to recall a small geometry lesson, and let's recall that when we have a point and we also have a line, the line for it, then the set of points that are equally distant from both the point and the line form parabola. Why do we need it? Well, we need it because the beach line that I already told you a few words about it is a sequence of exactly those parabolas that are that have been developed by given points and the sweep line. So two observations. The beach line is x monotone, as you can see here. This is the beach line here. This is x monotone. And the second observation is that the breakpoints between arcs are exactly on edges of Voronoi diagram. How does it happen exactly? This happens because when you look at this breakpoint, for example, between point B and C, you can see that this point is equally distant to B and the sweep line, and at the same time, it's equally distant to sweep line and C, which means it's equally distance between B and C, which leads us into the final assumption that this point is equally distant from those 2 points, which is exactly the definition of the Voronoi edge. When we are on the Voronoi edge, we know that we are equally distant from 2 sides. Well, this is a very important thing we have to keep in mind for later. So how can the beach line change? There are exactly 2 cases when the beach line can change. And one is when the new point passes the sweep line, as shown here. We can see the first image, and like millimeter later, we encounter the F point, and we see that this new point passes the sweep line, and we have a new arc here. And the second case when the sweep line changes is when the one arc disappears. I will show you it later as well, but you can see it here that previously the arc for the point E was important because it was a part of the beach line, but right now with this point F, we can see that this arc is hidden from the sweep line, so we do not look at it anymore. Okay, so the side event, let's look at it. Let's look at it more closely. When the new parabola arrives, like this one did here, at first it's very thin, like here, and then it gets wider and wider. And this lemma says that it is a very important lemma for the implementation. I will not prove it now, but let's just read it. That the only way in which a new arc can appear on the beach line is through a side event. This event, I mean when the new parabola arrives, it's called side event. And we have a second type of event. This is circle event, and they happen when the parabola disappears, which I also told you before. So let's look at this orange rectangle. You can see that there was this little part of arc which doesn't really look like arc because it's really wide, and then it really disappeared, and we call it circle event. And why do we call it exactly circle event? Why? Well, we call it circle event because when this parabola disappears and we have this breakpoint here, we can trace a circle which goes through those three sides, which is centered at this breakpoint, and which also goes through the sweep line. That's why it's a circle event. And we have a different lemma. The only way in which an existing arc can disappear from the beach line is through a circle event. Again, I will not prove it now in those 3 minutes I have left. Okay, so how to store information about the beach line? We will need a data structure that stores the part of the Voronoi diagram computed so far, and this of course will be our famous D cell. And we also need some, let's call it standard, according to the sweepline paradigm, data structures to store a priority event queue and the structure that will represent our beach line. So in order to keep it, to have this n log n time running, we have to keep the beach line as a balanced binary search tree whose leaves correspond to the arcs and whose internal nodes correspond to the breakpoints on the beach line. And we also have an event queue, which is a priority queue with the y coordinate that will store upcoming events, either side event or circle events. There's one issue. We have to make sure that we will pass through all desired events, although it's very easy to be sure that we will pass all side events because they are just our sides. We have to make sure somehow that we will pass through all the circle events. So at each time we will encounter one event, we'll have to search for possible triples that may or may not converge, and add those possible convergence to the circle events to the queue. Later, maybe we will change those events to false if needed. So this is the algorithm's implementation. We have to first initialize our queue, our D cell, and of course our tree structure that will hold the beach line. And while the queue is not empty, we have to pop the events. If the event is side event, then we have to handle side event. Else we have to handle the circle event. At both handlings, we have to maintain both the tree structure and the events queue. We have to check for new possible triples of consecutive arcs for the breakpoints converge at any time we have a new arc. And if we find such a triple that may converge in future, we will add it to the events queue. At the handle circles event, we have to delete the leaf from the tree structure. We have to update the tuples and the internal nodes in the tree structure. We have to update our D cell, and most importantly, we have to check if there is a new triple of consecutive arcs for converge, and we have to update them if needed. The summary is as follows. The algorithm runs in n log n time and uses linear storage. Operations on T and Q take logarithmic time. There are n-side events, which is very obvious, but the number of circle events is not this obvious. Well, I will prove it that this is linear number because exactly the number of vertices in Voronoi diagram is equal to number of circle events, because every time we will process the circle event, we are sure that this event is one vertex in Voronoi diagram. All the rest will be set to false, and we know that number of vertices in Voronoi diagram is linear, so this number of circle events is linear as well. So in all, we have linear number of events, which give us n times log n, which give us n log n.